Planck satellite circling in the deep chill of space had just sent back its latest batch of data. Dr. Catherine Jones zoomed in on a specific region, a vast cold patch spanning billions of light years, when an anomaly flashed across her screen. It wasn't just cold, it was *2* cold, defying the uniform expectations of the cosmic microwave background. Something colossal, something profoundly unsettling, was lurking at the very edge of the observable universe. The alarm triggered at 3:47 a.m., but it wasn't a malfunction, it was the data. Across a dozen screens in the command center, the European Space Agency's Planck Observatory had identified an unprecedented irregularity in the cosmic microwave background. Dr. Elias Vance, head of the CMB analysis team, stared at the flickering map, his coffee long forgotten as the implications began to dawn. This was not a subtle deviation, it was a profound, enormous imprint across the oldest light in the universe. The uniform cosmic canvas was anything but. What they were seeing challenged decades of established cosmology, indicating a universe far stranger than previously imagined. The satellite, positioned far from Earth's interference at the second Lagrange point, had meticulously mapped the faint afterglow of the Big Bang. But instead of the perfectly random, isotropic patterns predicted by standard models, a peculiar alignment was emerging. This wasn't just noise, it was structure, and its presence hinted at fundamental flaws in our understanding of cosmic origins. The team knew immediately that these weren't instrumental errors or statistical flukes. The signal was robust, persistent, and undeniable. It suggested that our universe might have a preferred direction, or perhaps even an unusual shape directly imprinted upon its earliest light. For the first time, scientists were confronted with evidence that the very fabric of spacetime, moments after its birth, held secrets far beyond our current comprehension. The cosmic microwave background, our universe's baby photo, was hiding something spectacular. The cosmic microwave background, or CMB, is the oldest light in the universe, a faint echo of the Big Bang itself. It was discovered accidentally in 1964 by Penzias and Wilson, earning them a Nobel Prize. This uniform glow saturates all of space, representing the moment about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to form neutral atoms. This allowed photons, previously trapped in a dense plasma, to stream freely for the first time. Before this epoch, the universe was an opaque, scorching hot fog, but the CMB captures the temperature fluctuations in that primordial plasma. These minuscule variations, only tens of microkelvins, represent the seeds from which all future structures, galaxies, stars, and ultimately you, would eventually grow. Scientists use satellites like WMAP and Planck to map these tiny temperature differences across the entire sky. This map is the blueprint of our cosmos, yet it contains profound mysteries that continue to baffle researchers. The standard cosmological model, known as lambda-CDM, predicts a universe that is largely isotropic and homogeneous on large scales, meaning it looks the same in all directions and everywhere. This model has been incredibly successful, explaining much of what we observe, but the CMB maps reveal persistent anomalies. These unexplained features challenge our most fundamental assumptions about the universe's beginning and its overall structure. Let's delve into 10 of these mind-bending enigmas. Number 1, the cold spot. This is an enormous region in the southern celestial hemisphere, appearing significantly colder than its surroundings in the CMB map. Discovered by the WMAP satellite, this vast area spans over 1 billion light-years across. Its temperature deviation is about 70 microkelvins below the average, which is statistically improbable within the standard cosmological model. The probability of such a large, cold region arising from random fluctuations is estimated to be less than 1 in 50,000. One leading hypothesis for the cold spot is the presence of a supervoid, an enormous region of space with far fewer galaxies than average. However, even the largest known supervoids don't fully explain the observed temperature drop. Another, more exotic theory suggests it might be the result of a collision between our universe and another, bubble universe, during the early universe. This specific anomaly strongly hints that our cosmological model might be incomplete, pushing scientists to consider truly bizarre explanations. Number 2, the axis of evil. This captivating anomaly refers to an alignment of the CMB's largest fluctuations along a particular direction in space. Discovered by the WMAP satellite and later confirmed by Planck, this alignment roughly coincides with the ecliptic plane, the plane of Earth's orbit around the Sun. The existence of such a preferred direction contradicts the principle of cosmological isotropy, which states the universe should look the same in all directions. It suggests a fundamental asymmetry. The axis of evil is highly controversial because if it's not a statistical fluke, it suggests that either our universe has a peculiar large-scale structure or our telescopes are somehow biased. While some argue it could be an observational artifact, sophisticated analyses have failed to fully dismiss it. This puzzling alignment challenges the fundamental assumption that the universe is isotropic, potentially pointing to new physics or a deeper connection between our local cosmic neighborhood and the vast universe. Number 3, anomalous low-L power. The CMB power spectrum measures the amplitude of temperature fluctuations at different angular scales across the sky. At the largest angular scales, the lowest L values, the observed fluctuations are significantly weaker than predicted by the standard lambda-CDM model. This suppression of power implies that the largest structures in the early universe were less pronounced than expected, a curious deviation from theoretical predictions. This unexpected dip in power, particularly at dipole and quadrupole moments, has puzzled cosmologists for years. While cosmic variance, the idea that we only observe one realization of the universe, might play a role, its persistent nature suggests something more fundamental. Some theories propose that this anomaly could be evidence of a non-trivial topology of the universe, meaning it might not be infinitely large and flat, or even that inflation had a different, unexpected phase. Number 4, hemispherical asymmetry. The CMB map exhibits an unexpected imbalance in the average temperature fluctuations between opposite hemispheres of the sky. Specifically, one hemisphere shows significantly larger temperature variations than the other. This anisotropy contradicts the cosmological principle, which postulates that the universe is homogeneous and isotropic on scales larger than about 100 megaparsecs. It implies a preferred direction for the strength of cosmic structures. This hemispherical asymmetry is not easily explained by standard physics and remains a stubborn statistical anomaly, appearing at a significance level of several standard deviations. Potential explanations range from fundamental properties of dark energy or dark flow to the possibility of a non-standard inflationary period that imparted a preferred direction to the cosmos. It challenges the very idea of a perfectly uniform and statistically random early universe, suggesting an inherent cosmic tilt. Number 5, lack of large-angle correlations. Another peculiar feature in the CMB is the unexpected absence of temperature correlations at angles greater than about 60 degrees. You pick 2 points on the CMB sky separated by more than 60 degrees, their temperatures should still show some statistical correlation according to the lambda-CDM model. However, observations from both WMAP and Planck show these correlations are much weaker than predicted. This missing correlation on large angular scales suggests that the universe might be smaller than we think or have a peculiar shape. If the universe had a finite, non-trivial topology, it could suppress these large-scale correlations by making certain paths around the universe shorter than expected. Alternatively, it could point to limitations in our understanding of the very early universe, potentially requiring modifications to inflationary theory to accommodate this statistical oddity. Number 6, CMB lensing anomalies. Gravitational lensing, where the paths of light are bent by massive objects, also affects the CMB. The distribution of matter in the universe gravitationally lenses the CMB photons as they travel towards us, distorting the patterns. Scientists can precisely predict how much lensing should occur based on the standard model, but some observations show discrepancies in the observed lensing potential. This indicates an unusual distribution of dark matter. These subtle deviations in CMB lensing maps, particularly in certain regions, suggest that our understanding of the large-scale distribution of dark matter might be incomplete. They might hint at variations in the universe's matter density that are inconsistent with a perfectly smooth distribution, or even point to new forms of dark matter or modified gravity theories. Investigating these lensing anomalies could unlock profound insights into the mysterious nature of dark matter and dark energy. Number 7, evidence of cosmic strings. Cosmic strings are hypothetical, one-dimensional topological defects predicted by some theories of particle physics beyond the standard model. They existed in the early universe. These incredibly dense, thin filaments of energy would leave specific, characteristic imprints on the CMB. These imprints would manifest as sharp, linear discontinuities in temperature and polarization, different from the smooth fluctuations caused by sound waves. Despite dedicated searches, no definitive evidence of cosmic strings has been found in the CMB data so far, which places strong upper limits on their possible existence. However, the theoretical possibility remains tantalizing, as their detection would provide a direct link to physics at extremely high energies during the universe's birth. Future, more sensitive CMB experiments continue to refine these limits, pushing the boundaries of what we can discern about the universe's most exotic primordial features. Number 8, circular polarization. The CMB is primarily linearly polarized, meaning its light waves oscillate in a specific plane. However, the detection of circular polarization, where the light waves spiral as they propagate, would be a monumental discovery. Standard cosmological models predict that the CMB should have essentially zero circular polarization, as the early universe was largely transparent and lacked processes to generate it. Its presence would signify entirely new physics. The detection of circular polarization in the CMB would imply the existence of incredibly strong primordial magnetic fields or even exotic chiral gravity theories that favor a particular handedness in the universe. Such a discovery would fundamentally alter our understanding of the universe's earliest moments and its fundamental symmetries. While current observations place stringent upper limits on circular polarization, the search continues, as even a tiny signal could unravel immense cosmic secrets. Number 9. Primordial gravitational waves, B-modes. Inflationary theory, which posits a period of extremely rapid expansion just after the Big Bang, predicts the existence of primordial gravitational waves. These waves would leave a unique swirling pattern known as B-mode polarization in the CMB. Detecting these B-modes would be direct evidence of inflation and provide crucial insights into the physics of the universe at its absolute beginning. The hunt for primordial B-modes has been intense, famously leading to the BICEP 2 collaboration's controversial announcement in 2014, which was later retracted as foreground dust. Nevertheless, experiments like Planck, the Atacama Cosmology Telescope, and the South Pole Telescope continue to refine their measurements. A definitive detection of B-modes, despite the immense technical challenges, remains one of the holy grails of cosmology, promising to unlock secrets about the universe's first fleeting moments. Number 10. The Hubble tension. While not a direct CMB anomaly, the CMB provides the most precise early universe measurement of the Hubble constant, which describes the universe's expansion rate. This value, derived from Planck data, is around 67.4 kilometers per second per megaparsec. However, independent measurements from the late universe, using observations of local supernovae and other distance ladders, consistently yield a higher value, closer to 73. This persistent 8–9% discrepancy, known as the Hubble tension, is one of the most significant crises in modern cosmology. It suggests that either there are unknown systematic errors in one or both sets of measurements, or more thrillingly, that our standard lambda-CDM model is incomplete. The tension might be hinting at new physics, such as unknown particles, modified gravity, or a different form of dark energy, impacting the universe's expansion history. Resolving this tension is paramount. These 10 mysteries, etched into the oldest light in the cosmos, are not mere footnotes. They are direct challenges to our most cherished understanding of the universe. Each anomaly, from the vast cold spot to the perplexing Hubble tension, pulls at the threads of the standard cosmological model. They force scientists to question whether our current theories are sufficient to explain the universe's grand design. The pursuit of these answers pushes the boundaries of human ingenuity, driving the development of new telescopes, more sensitive detectors, and more sophisticated theoretical models. Every new satellite, every improved analysis technique brings us closer to unraveling these cosmic enigmas. The CMB is not just a relic, it's a dynamic puzzle board, constantly revealing new clues about our origins. What we learn from these mysteries could rewrite textbooks and reshape our perception of reality itself. Whether these anomalies are statistical flukes, instrumental errors, or genuine evidence of new physics, one thing is certain: the universe is far more complex and intriguing than we ever dared to imagine. Its baby photo holds secrets to its entire life story, and we are only just beginning to read them. If you found these cosmic conundrums as mind-bending as we did, make sure to hit that like button and subscribe for more deep dives into the universe's greatest secrets. What do you think is the most plausible explanation for these CMB mysteries? Share your thoughts and theories in the comments below. Your insights might just spark the next great debate.